third part of this bending derivation work. Really the rod point formula. Just to kind of review where we've been, we assumed that when we formed, we assumed some deformation shapes, schematics if you will, that the cross section is remain in the plane and perpendicular to its neutral axis. Now the neutral axis, when we think about bending, it's rather obvious that you'll have an alternating, well, you'll have tension on one side and compression on the other side. And it's quite reasonable to assume that there's going to be one location through the thickness where we transition from tension to compression. In other words, the strain is equal to zero, and therefore the stress is equal to zero. Using that, we're able to show that the strain distribution for the cross section minus y over rho, which is the radius of curvature. I don't know what the radius of curvature is, and also really don't know the location of this neutral axis. Now, the next thing we did was we looked at sum of forces. We did sum of forces in the x direction. This didn't give us really an equation per se, but showed that the location of the central axis, the neutral axis, has to correspond to the location of the centroid cross section. So if this is the cross section of the beam, negative, in and out of the board, and it comes out of the page, then the centroid, area centroid cross section is where the strain goes to zero. That's the location of the neutral axis. Okay. Oh, right. And basically what that means is if you look at the following equation. If you have the centroid, that means that the area above the if you think about the centroid, it means that there's equal area above as opposed to below. And the area, area of the first wave is area minus. So what you see here is the distribution. Basically, this is saying the tension forces on one side balance the compression forces on the other side. Okay? But anyway, set neutral axis corresponds to the centroid. Sum of forces in the y are trivially solved. The last thing we have to talk about is the sum of moments for equilibrium. That's what's going to give us the question. So let's look at that. Let's look at the sum of moments in the cross section. Actually, we can use this same free body line. So here we go. Here's our cross section. Let's do. It doesn't matter. So sum of moments from that point to neutral axis. This is actually the z-axis. We'll call it 1. And so what happens here is we have the internal reaction moment here, the f of x. That's on a negative face the way I've drawn that. So I'm going to negative f of x. And that has to, add the effective moments that you get across this shape. Okay? So look at this cross section. You have this stress distribution. Each one of these little differential stresses produce a moment. So I'm going to write that just for now. So we're going to go over the area. But this is the moment produced by internal stresses. That makes sense, because if you look at it, let's aggregate the tensional stresses, the tensional stresses at the bottom, and the compressional stresses at the top. So the tension stresses are going to act this way, and through some point effectively below the neutral axis. Compressional stresses are going to act this way, in the negative x direction, above the neutral axis. And if you look at these two forces, you can see that produces a couple. There's a couple. And it's going to balance out the internal reaction force. All right? So I'm going to figure this out. The net effect of that, the stress, and that's the let's look at the cross section a little more closely. Here's that cut face. Here's the location of the neutral axis. And we know that the stress alternates as follows. The tension side, the compression side. Let's just look at some point y, the positive location y. There is a differential force at the x. Okay? That's the differential force from the normal stress at that point. So that equals the normal stress times the differential area, correct? That's the force, stress times area. The differential force is the stress times the differential area. Now this produces a moment around point O, and its moment arm is y. So the differential moment is positive, right? This way. That's a positive moment. The differential moment is differential force times y, and here we get sigma y. Now if I take that, put it into here, what do we get? Now we have the moment, bring this on the right-hand side, is equal to the integral over the area. So this internal reaction moment is equal to the integral over the area of the differential moment, which is stress times y. Now we know the stress, right? The stress distribution. Stress is a function of y. This is equal to Young's modulus times the strain. So this is going to be minus y over so let's put that in here. Stress integral over the area minus y squared over rho. Now, oops, I'm sorry. No y here, no y here. So y squared. I said y squared. There you go. Now, okay, I'm doing a little different as well. Let's do this. This is fine. And so I can take the e and the rho out. They're constant over in cross section. So minus e on rho times a y squared. Now again, this looks a lot like torsion type of equation. What we can see here is a parameter that has entirely to do with geometry, geometric distribution of the cross section. Look over the cross section of the beam. This integral deals with differential area times y. It's the integral of dA over y. So it has to do just with the geometry of the cross section. It's like J, and we call this one I. Okay? So it's a rectilinear area. Okay? We call it the second area. All right. So now we got a relationship. We're going to call it I. So now we know that bending moment equals minus rho times this geometric quantity. All right. Well, now I can actually get the radius of curvature, or the curvature. We can do a little manipulation here. You know the curvature is equal to 1 on rho. So that's got to equal internal bending moment over I with an x. Now if I take this, so let's actually just put the relationship. We'll use that later on when we talk about the deflection in chapter 10, I think so. There it is. Now now that I know rho, in terms of the bending moment of E I, I put that back into the stress distribution equation. If I take this, put it into this equation, what do I obtain? I get the following. I get that the stress, function of y, is equal to E on rho minus E on rho. So E on rho, I multiply this by E, x I times y. Whenever I do this derivation, I always end up screwing up and dropping some. I don't know why I do this. But anyway, so what this is telling us now is that the stress, which is a function of y, and the internal bending moment times the distance from the neutral axis over this geometric quantity pi. It should be a negative. The reason it should be negative is because as you go up in y, the positive bending moment should be compression. Whenever I do this, I always drop a sign somewhere. Whenever I drop the sign, let's see if I can see it real quick. This is right. The signs on this are right. Stress. This produces positive one. Okay. But it only produces the positive side. It only produces the positive moment. It's only going in this direction when the stress is negative. So actually, it should be a negative sign on that. Okay. So if it's a negative, this means this positive. This is positive. This is positive. This is positive. Which puts a negative. Okay. Draw the picture. So anyway, this is going in a positive sense only when the stress is negative. Right? Really, a positive stress would go out this way. So df, right? A positive stress is going this way. That actually proves that negative stress times. Well, I'm sorry, that's right. But it's drawn the wrong way. It's drawn with minus df times y. All right. All right. Sorry about that. I should go fix the video at some point in time when I have nothing else to do. But anyway, this is now our flexure formula. So let's just talk about it. This is very significant. I should probably write it a little more neatly. Okay. So this is going to relate. See, now we can determine the internal normal stresses in the beam cross section. Function of y. So I can determine this stress distribution. Okay, linear. It's related to the distance from the neutral axis, y. The value of the internal bending moment at that point. Okay, so if you know the internal bending moment from, say, a bending moment diagram, right? That goes in here. And then if you know I, which you can compute, that's the integral over the cross-sectional area of y squared. I'll do another video where we actually compute that for some standard shapes like a rectangle. If you have a rectangular shape like this, and this is the I is the base times the height to the third power over 12. I'll divide that. That's good enough to get you going on this problem. So you should memorize that. Very similar to J, which is pi over 32 diameter of 4. In this case, it's again going to have units of length to the fourth, okay? Meters to the fourth, inches to the fourth. Base times the height cubed over 12. Okay, so you know I, this relates the stress to the internal bending. All right? So, just as a real quick example. Oh, okay, I should mention that. And then what you can see, obviously, is you get the maximum stress here. This is the max tension stress. This is the max bending stress. I'm sorry, the max compression stress. Now, if the cross section is symmetric, that means the neutral axis passes right through the middle. The distance to the top equals the distance to the bottom. We call it C and C. What you can see is that the stress here has to equal the negative of the stress of the bottom. So the stresses, then the tensional stresses are equal to the negative of the tensional stresses. Okay? You won't always have that situation. Okay? In general, you might have a cross section that is not symmetrical. The bottom flange might be a little smaller than the top flange, or something like that. Right? If that's the case, then the neutral axis will be, in this the way I've drawn this here, the neutral axis will be closer to the top. So that means you'll have different distances to the outer fibers. We'll call it C1 and C2. Now in that situation, think about it, the maximum stress will occur here. That's the maximum absolute value of the stress. Why? Because the y distance to here is greater than the y distance to here. On this cross section, I is the same. On the cross section, M is the same. The only thing that changes is y. And what we're saying here is you go to the point on the cross section farthest away from the neutral axis. That's where the maximum stress will be. Now, this might be tension or it might be compression. You don't know until you know the signs of bending. So that's it. I was going to do a simple problem. I've got to go to a meeting, but let's see if I can do this real quick. So, okay, let's just do, here's the cantilever beam. All right, let's put 100 pounds on the right side. Let's make the numbers. Let's make this 24 inches. All right. It has a cross section. Let's say 4 inches high, 2 inches wide. Okay, so that's the cross section. Let's find the maximum bending stress. Okay, we know that I for this geometry is 1/12 base times height. In this case, the base is 2 inches. The height is 4 inches. Base times height is 4 over 12. I should have my calculator. about the bending moment? Well, we can look at this, and we've done this problem before. We know that the bending moment function x, max is going to be here. Bending moment in this case is show 100 pounds. This distance here is 24 minus x. Shear this way is actually positive shear. Constant. Bending moment is positive in this direction. But that has to equal minus 100 pounds times 24 minus x. Right? So if we draw the bending moment diagram, the maximum value is at x equals 0, where the base bending moment diagram. This is a negative bending moment is x. This is 10, where x equals 24 inches. Right? So this value here, the maximum bending moment is right at this point, the blue, and that has a value of 2,400 pound inches, negative 2,400 pound inches. Right? Just putting an x equals 0 here. All right. So the maximum bending moment occurs there. Now the maximum bending stress will occur there as well because bending stress on the whole beam, right? You can see I is constant for the whole beam. So the maximum bending stress is going to occur where the bending moment is max. So it's at this point. So it's going to occur in outer fiber distances. Here, here. Now, this beam is symmetric, so the distances to the top fiber are the same as the distance to the bottom fiber. It's 2 inches in both cases, all right? And so this side is going to be tension, and this side is going to be compression, right? But anyway, let's put that into the equation so we know that the stress, let's do it on the tension side. So this is at y equal to 2 inches, positive 2 inches. That's going to equal the bending moment, which is minus 2,400, and we got minus times a minus, so it's going to be 2,400 pound inches. Y is 2 inches. And we've already figured out that I is 10.7 inches to the fourth. Okay? So the negatives cancel out. And now I'm left with 2,400 2 times 10.75 gives me stress there is equal to 448 psi. Right? Now the stress at the bottom side is going to be negative 448 psi. Okay? All right, that's the end of